Q192. ANS. Illustrate the distinctions that characterize rivers in northern and southern regions of India. 10 marks, 150 words, core demand of question. Provide the distinctions that characterize rivers in northern and southern regions of India and substantiate with relevant examples. The Indian drainage system is characterized by a complex network of rivers, lakes, and other water bodies that play a crucial role in shaping the country's geography and supporting its agriculture and economy. However, it is divided into northern and southern river systems that share similarities in their fundamental importance for agriculture, transportation, and ecological diversity. Despite these commonalities, northern and southern river systems possess distinct characteristics, as provided below. Distinctions characterizing the rivers in northern and southern regions of India. Characteristics: northern rivers, southern rivers, origin mainly Himalayas and northern mountain ranges, including glaciers, e.g., Ganga originating from Gangotri Glacier, Western Ghats and Deccan Plateau, e.g., Godavari originating from Trimbak Hills, water source snowmelt, glaciers, and rainfall, e.g., Brahmaputra, rainfall and runoff from Western Ghats, e.g., Tungabhadra, type of river mostly antecedent exemplified by Indus, Satluj, Ganga. Mostly consequent exemplified by Godavari, Krishna, Kaveri. Flow direction: generally flow towards the Bay of Bengal, e.g. Brahmaputra. Most of the major peninsular rivers flow towards the Bay of Bengal except Narmada and Tapi, which flows towards the Arabian Sea. Water availability: mostly perennial rivers, e.g. Yamuna. Mostly seasonal, e.g. Krishna. Development of canals: more developed as they pass through plain areas, e.g. Ganges Canal. Comparatively less development of canals due to the harder plateau regions, e.g. Kaveri River, flowing through the Deccan Plateau. Erosion and sediments carry more sediment and contribute to the prominent formation of deltas, e.g. Ganges Brahmaputra have formed largest river delta of the world. The Sundarban Delta carry fewer sediments and exhibit less prominent delta formation, as seen in rivers like the Mahanadi with its comparatively smaller delta. Flood patterns: prone to seasonal floods during monsoons, e.g. Brahmaputra. Lesser tendency for severe monsoon flooding, e.g. Tapi. Characteristics: northern rivers, southern rivers, hydroelectric potential, high possibilities for the development of hydropower projects, e.g. Sutlej. Limited due to tough terrain and seasonal water availability in rivers, e.g. Sharavathi. Navigation: high potential, as these are perennial and travel long distances, e.g. Ganga. Limited due to seasonal flow and hilly terrain, e.g. Periyar. Landforms: form a large number of landforms like V-shaped valleys, gorges, canyons, alluvial plains. For instance, the Brahmaputra River forms a gorge near Namcha Barwa in Tibet, known as the Tsongpa Gorge. Form comparatively less landforms like waterfalls, e.g., Sharavathi River has formed the Jog Falls in Karnataka. Stages of river: all three major stages viz., youthful, mature, and old can be seen, as illustrated by the river Yamuna. 3 stages of rivers are not clear. Especially the youth stage is absent, as showcased by the river Kaveri. Meandering: extensive meandering sections, as demonstrated by the rivers Ganges, Yamuna, and Brahmaputra. Shorter meandering sections, as exemplified by the rivers Godavari, Krishna, and Kaveri. Dispute: international, illustrated by the Brahmaputra River dispute between India and China. Interstate, exemplified by the Kaveri River dispute between the states of Tamil Nadu and Karnataka. In the intricate tapestry of India's rivers, the distinctions that mark the northern and southern regions form a dynamic symphony of nature's diversity. These distinctions, rooted in geography, origin, flow patterns, and ecological characteristics, weave a complex narrative that influences our nation's landscape, economy, and culture. By embracing the uniqueness of each river system, we can pave the way for sustainable development, equitable water sharing agreements, and the preservation of our natural heritage. Q193. What geological processes led to the formation of the Deccan Traps, and how do they offer insights into Earth's history? 15 marks, 250 words, core demand of question. Write about the geological processes which led to the formation of the Deccan Traps. Write how do they offer insights into Earth's history. ANS. The Deccan Traps are a huge volcanic province in India. They formed from fissure eruptions of basalt lava 66 million years ago. They cover about 500,000 square kilometers and are divided into 3 units. These formations cover a substantial portion of the Deccan Plateau and have raised questions about their origins and implications for our understanding of the planet's past. Geological processes leading to the formation of the Deccan Traps. Volcanic activity. The genesis of the Deccan Traps can be traced back to massive volcanic eruptions that occurred approximately 66 million years ago during the late Cretaceous period. These eruptions, of an unprecedented scale, played a pivotal role in shaping the plateau. Basaltic lava flows. These eruptions predominantly featured basaltic lava, characterized by its low viscosity. This property allowed the lava to flow across vast distances before eventually solidifying. As a result, extensive layers of basaltic rock formed. Flood basalts. The Deccan Traps earned their classification as flood basalts due to the staggering volume of lava discharged during the eruption phases. These floods of lava inundated the region, resulting in the expansive plateau we witness today. Cracking of the Earth's crust. The volcanic activity was triggered by the rifting or cracking of the Earth's crust. This process created conduits for molten rock to ascend from the Earth's mantle to the surface, setting the stage for colossal eruptions. Hotspot theory. This theory posits the existence of a mantle plume, an upwelling of exceptionally hot rock from the Earth's mantle, located beneath the Indian plate. The heat generated by this plume led to the melting of the Earth's crust, giving rise to volcanic activity. Multiple eruption phases. It did not arise from a single cataclysmic event, but instead emerged through numerous eruption phases spanning thousands of years. These episodic eruptions deposited layer upon layer of basaltic rock, some exceeding thicknesses of 2 kilometers. Massive outpouring. During each eruption phase, immense quantities of lava were released. This deluge of molten rock contributed to the stratified nature of the Deccan Traps, with each layer representing a distinct eruption episode. Interplay with Q194toQ214. Illustrate the distinctions that characterize rivers in northern and southern regions of India. 10 marks, 150 words, core demand of question. Provide the distinctions that characterize rivers in northern and southern regions of India and substantiate with relevant examples. The Indian drainage system is characterized by a complex network of rivers, lakes, and other water bodies that play a crucial role in shaping the country's geography and supporting its agriculture and economy. However, it is divided into northern and southern river systems that share similarities in their fundamental importance for agriculture, transportation, and ecological diversity. Despite these commonalities, northern and southern river systems possess distinct characteristics, as provided below. Distinctions characterizing the rivers in northern and southern regions of India. Characteristics: northern rivers. Southern rivers origin mainly Himalayas and northern mountain ranges, including glaciers, e.g., Ganga originating from Gangotri Glacier. Western Ghats and Deccan Plateau, e.g., Godavari originating from Trimbak Hills, water source snowmelt, glaciers, and rainfall, e.g., Brahmaputra. Rainfall and runoff from Western Ghats, e.g., Tungabhadra. Type of river mostly antecedent exemplified by Indus, Satluj, Ganga. Mostly consequent exemplified by Godavari, Krishna, Kaveri. Flow direction generally flow towards the Bay of Bengal, e.g. Brahmaputra. Most of the major peninsular rivers flow towards the Bay of Bengal except Narmada and Tapi, which flows towards the Arabian Sea. Water availability: mostly perennial rivers, e.g. Yamuna. Mostly seasonal, e.g. Krishna. Development of canals more developed as they pass through plain areas, e.g. Ganges Canal. Comparatively less development of canals due to the harder plateau regions, e.g. Kaveri River, flowing through the Deccan Plateau. Erosion and sediments carry more sediment and contribute to the prominent formation of deltas, e.g. Ganges, Brahmaputra have formed largest river delta of the world. The Sundarban Delta carry fewer sediments and exhibit less prominent delta formation, as seen in rivers like the Mahanadi with its comparatively smaller delta. Flood patterns: prone to seasonal floods during monsoons, e.g. Brahmaputra. Lesser tendency for severe monsoon flooding, e.g. Tapi. Characteristics: northern rivers, southern rivers. Hydroelectric potential: high possibilities for the development of hydropower projects, e.g. Sutlej. Limited due to tough terrain and seasonal water availability in rivers, e.g. Sharavathi. Navigation: high potential, as these are perennial and travel long distances, e.g. Ganga. Limited due to seasonal flow and hilly terrain, e.g. Periyar. Landforms: form a large number of landforms like V-shaped valleys, gorges, canyons, alluvial plains. For instance, the Brahmaputra River forms a gorge near Namchabarwa in Tibet, known as the Tsongpa Gorge. Form comparatively less landforms like waterfalls, e.g., Sharavati River has formed the Jog Falls in Karnataka. Stages of river. All three major stages, viz., youthful, mature, and old, can be seen, as illustrated by the river Yamuna. 3 stages of rivers are not clear, especially the youth stage is absent, as showcased by the river Kaveri. Meandering. Extensive meandering sections, as demonstrated by the rivers Ganges, Yamuna, and Brahmaputra. Shorter meandering sections, as exemplified by the rivers Godavari, Krishna, and Kaveri. Dispute. International, illustrated by the Brahmaputra River dispute between India and China. Interstate, exemplified by the Kaveri River dispute between the states of Tamil Nadu and Karnataka. In the intricate tapestry of India's rivers, the distinctions that mark the northern and southern regions form a dynamic symphony of nature's diversity. These distinctions, rooted in geography, origin, flow patterns, and ecological characteristics, weave a complex narrative that influences our nation's landscape, economy, and culture. By embracing the uniqueness of each river system, we can pave the way for sustainable development, equitable water-sharing agreements, and the preservation of our natural heritage. Q193. What geological processes led to the formation of the Deccan Traps, and how do they offer insights into Earth's history? 15 marks, 250 words, core demand of question. Write about the geological processes which led to the formation of the Deccan Traps. Write how do they offer insights into Earth's history. ANS. The Deccan Traps are a huge volcanic province in India. They formed from fissure eruptions of basalt lava 66 million years ago. They cover about 500,000 square kilometers and are divided into 3 units. These formations cover a substantial portion of the Deccan Plateau and have raised questions about their origins and implications for our understanding of the planet's past. Geological processes leading to the formation of the Deccan Traps. Volcanic activity. The genesis of the Deccan Traps can be traced back to massive volcanic eruptions that occurred approximately 66 million years ago, during the late Cretaceous period. These eruptions, of an unprecedented scale, played a pivotal role in shaping the plateau. Basaltic lava flows. These eruptions predominantly featured basaltic lava, characterized by its low viscosity. This property allowed the lava to flow across vast distances before eventually solidifying. As a result, extensive layers of basaltic rock formed. Flood basalts. The Deccan Traps earned their classification as flood basalts due to the staggering volume of lava discharged during the eruption phases. These floods of lava inundated the region, resulting in the expansive plateau we witness today. Cracking of the Earth's crust. The volcanic activity was triggered by the rifting or cracking of the Earth's crust. This process created conduits for molten rock to ascend from the Earth's mantle to the surface, setting the stage for colossal eruptions. Hotspot theory. This theory posits the existence of a mantle plume, an upwelling of exceptionally hot rock from the Earth's mantle, located beneath the Indian plate. The heat generated by this plume led to the melting of the Earth's crust, giving rise to volcanic activity. Multiple eruption phases. It did not arise from a single cataclysmic event, but instead emerged through numerous eruption phases spanning thousands of years. These episodic eruptions deposited layer upon layer of basaltic rock, some exceeding thicknesses of 2 kilometers. Massive outpouring. During each eruption phase, immense quantities of lava were released. This deluge of molten rock contributed to the stratified nature of the Deccan Traps, with each layer representing a distinct eruption episode. Interplay with. Resistant technologies is still lacking in India. Microzonation maps, which are essential for understanding region-specific seismic vulnerabilities, are yet to be developed for many cities. Coordination. The necessity for seamless communication and collaboration, evident from the challenges faced during the Sikkim earthquake in 2011, underlines the importance of streamlined processes for efficient disaster response. Resettlement issues. The complexities associated with relocation were evident in the aftermath of the Latur earthquake in 1993, where the establishment of a new settlement confronted several logistical and socio-cultural issues, showcasing the multifaceted challenges in rehabilitation efforts. As India marches towards sustainable development, embedding earthquake resilience into its urban and rural landscapes will be crucial. Implementing a multidimensional approach encompassing community participation, technological advancements, and global cooperation will be pivotal in steering the nation towards a safer future. Q195. Elucidate the reciprocity of tectonics and climate change as the primary drivers of landform evolution in the Himalayas. Also enumerate its implications for sustainable development and disaster risk reduction. 10 marks, 150 words, core demand of question. Mention about the reciprocity of tectonics and climate change as the primary drivers of landform evolution in the Himalayas. Mention its implications for sustainable development and disaster risk reduction. ANS. Landform evolution in the Himalayas refers to the changes in the landscape over time due to tectonic activity and climate change. It involves processes like uplift from plate collisions, glacial erosion and deposition, fluvial erosion, and landslide activity, all continually shaping the region. Reciprocity of tectonics and climate change as the primary drivers of landform evolution in the Himalayas. Plate tectonics. The Indian plate's collision with the Eurasian plate led to the formation of the Himalayas. This tectonic activity continues today, causing uplift and consequent erosion, exemplified by the creation of Everest's increasing height. Earthquakes. Resulting from tectonic movements, earthquakes reshape the terrain drastically, triggering landslides and causing river course changes. For example, the 2015 Gorkha earthquake in Nepal is an example, which led to significant landscape alterations. Glaciation. Climate change affects glaciation processes. Glaciers carve valleys and transport sediment, affecting topography. For example, the Gangotri Glacier's retreat due to global warming exemplifies the morphological changes brought by fluctuating glaciation. River erosion. Fed by glacial melt, rivers such as the Ganges and Brahmaputra erode the land, forming deep valleys and transporting sediment. These processes, modulated by climate patterns, sculpt the mountain ranges. Landslides. Both tectonics and climate changes contribute to landslides, which reshape the landform significantly. Monsoon rainfall, often intensified by climate change, along with seismic activity, can trigger massive landslides. For example, the 2013 Kedarnath disaster. Permafrost melting. Global warming leads to permafrost thawing in high-altitude areas. This changes the landscape by causing slope instability and landslides, increasing erosion and sediment delivery to rivers, evident in the Tibetan Plateau's changing landscapes. Altered precipitation patterns. Climate change modifies precipitation patterns, affecting erosional processes and river flow regimes, further reshaping the terrain. Increased monsoon intensity can lead to more soil erosion and landslides. Implications for sustainable development and disaster risk reduction. Infrastructure planning. Understanding the interplay between tectonics and climate change can guide infrastructure planning. Example, roads and bridges in landslide-prone areas, such as the Sutlej Valley, need extra reinforcement or alternate routing. Early warning systems. Knowledge of seismic and climate activities aids in developing early warning systems. For example, Nepal's flood forecasting system, which uses data on rainfall and river levels to predict flood events, exemplifies this. Agricultural practices. Changing climate patterns can affect agriculture. Sustainable practices like crop diversification can help farmers in regions like Ladakh adapt to changing glacial melt and monsoon patterns. Tourism management. As popular trekking routes become riskier due to increased landslide activity and glacial lake outburst floods, GLOFs, tourism management strategies need to adapt. For example, rerouting of treks in Nepal post the 2015 earthquake. Disaster risk reduction policies. Understanding geological processes can guide policies, like enforcing building codes resistant to earthquakes in seismic hotspots like Kathmandu. Adaptive urban planning. Cities like Gangtok, situated on hill slopes, must incorporate adaptive urban planning considering increased risks from climate change and seismic activity. Sustainable land use. With increasing incidence of landslides due to deforestation and land use change, sustainable land use practices become crucial. For example, in Sikkim, initiatives are being taken to stabilize slopes and promote forest regeneration. Q196. By understanding the interplay of tectonics and climate change, we can make more informed decisions about sustainable development and disaster risk reduction in the Himalayas. Like developing adaptive systems and policies, mitigating potential environmental disasters, and promoting resilience and sustainability in this globally important region. Highlight the significance of the Himalayas for realizing the Sustainable Development Goals, SDGs 2030. Discuss their natural resource potentials and the challenges in harnessing them. 15 marks, 250 words, core demand of question. Explain the significance of the Himalayas for realizing the SDGs 2030. Mention about the natural resource potentials of Himalayas. Enumerate various challenges in harnessing these resources. ANS. The Himalayas, often referred to as the roof of the world, is a mountain range located in South Asia, spanning across 5 countries. It is home to some of the world's highest peaks, diverse cultural communities, and unique biodiversity, making it a popular destination for adventure seekers and nature lovers. Significance of the Himalayas for realizing the SDGs 2030. Biodiversity hotspot. The Himalayas are a global biodiversity hotspot, with their diverse ecosystems supporting a wide range of plant and animal species. Conserving this biodiversity can help in achieving Goal 15, Life on Land. Climate regulation, Himalayan. Forests and vegetation act as carbon sinks and help mitigate climate change by absorbing greenhouse gases. Protecting these mountains is essential for SDG Goal 13, climate action, and SDG Goal 7, affordable and clean energy. Sustainable tourism. The Himalayas attract millions of tourists annually, providing opportunities for sustainable tourism development aligned with Goal 8, decent work and economic growth. Indigenous knowledge. Himalayas contains many indigenous communities like Gaddis, Bakarwals, etc. These communities have their own traditional knowledge. Integrating these indigenous knowledge and traditional practices of the region into policy making and development strategies can contribute to achieving Goal 4, quality education, and Goal 16, peace, justice, and strong institutions. Cultural heritage. Preserving and promoting the cultural heritage belonging to Himalayas contributes to Goal 11, sustainable cities and communities, and Goal 10, reduced inequalities, by fostering inclusive and sustainable development. Natural resource potentials of Himalayas. Water resources. The Himalayas are the source of major rivers in Asia, including the Ganges, Brahmaputra, and Indus, providing water for agriculture, hydropower generation, and drinking purposes to millions of people in the region. Minerals. The Himalayas are known to contain various minerals such as limestone, gypsum, quartz, copper, lead, zinc, and precious metals like gold and silver. Mining activities are carried out in regions like Jharkhand and Himachal Pradesh. Timber. The Himalayan forests are rich in diverse tree species, providing a significant supply of timber and other forest products. For example, Chur pine, deodar, oak, and maple, which are used for construction, furniture, and handicrafts. Medicinal plants. The Himalayas are a treasure trove of medicinal plants and herbs with various therapeutic properties. For example, neem, tulsi, aloe vera, and Himalayan yew, which are used in traditional medicine and pharmaceutical industries. Agriculture. The Himalayan foothills and valleys provide fertile land for agriculture. Staple crops like rice, wheat, maize, and millets are cultivated along with cash crops such as tea, apples, oranges, and spices like cardamom and ginger. For example, tea plantation in Brahmaputra Valley. Renewable energy. Apart from hydropower, the Himalayas have immense potential for other renewable energy sources such as solar energy, wind energy, geothermal energy, etc. For example, Puga geothermal field in Ladakh. Various challenges in harnessing these resources. Geographic complexity. Building roads and power transmission lines in the Himalayas is challenging due to steep slopes and frequent landslides. Water disputes, as mismanagement of water resources can lead to conflicts among countries sharing these rivers. The dispute over water sharing between India and Pakistan in the Indus River system is an example. Climate change vulnerability. The Himalayas are highly vulnerable to climate change, resulting in glacial melt, altered rainfall patterns, and increased frequency of natural disasters. For example, Chamoli disaster 2021. Illegal activities. The remote and inaccessible nature of the Himalayas makes it susceptible to illegal activities such as poaching, smuggling of wildlife products, and illegal mining. Disaster risks. The Himalayas are prone to earthquakes, landslides, and avalanches. This aggravates the risks associated with resource extraction and development in the region. For example, April 2023 avalanche in Indian Himalayas that killed 7 tourists. Thus, it is crucial to ensure that harnessing the natural resource potentials of the Himalayas should be done in a manner that preserves the region's unique ecology, cultural heritage, and benefits the local communities while minimizing negative impacts. Q197. Explain the mechanism behind the onset of the Indian monsoon. Additionally, explain the effect of YNSO on the Indian monsoon. 15 marks, 250 words, core demand of question. Discuss the mechanism behind the onset of the Indian monsoon. Describe the effect of YNSO, El Niño Southern Oscillation, on the Indian monsoon. ANS. Monsoon refers to a seasonal wind pattern characterized by a significant change in prevailing wind direction and intensity, which leads to distinct wet and dry seasons in certain regions, especially in the Indian subcontinent. In India, the southwest monsoon commences on the 15th of June, and the mechanism underlying its onset has been explained as follows. Mechanism behind the onset of the Indian monsoon. Differential heating. When the sun's rays strike the earth, different surfaces heat up at varying rates. During summer, land masses heat up faster than oceans. This causes the air above the land to warm and rise, creating a low-pressure area. Meanwhile, cooler air over the oceans creates a high-pressure area. Pressure gradient. The contrast in pressure between the land and the ocean generates a pressure gradient. Air flows from areas of high pressure, oceans, to areas of low pressure, land, initiating the movement of air masses. Intertropical Convergence Zone, ITCZ in summer, the ITCZ, a low-pressure belt encircling the Earth near the equator, migrates northward due to the sun's apparent movement. This displacement leads to the convergence of trade winds from both hemispheres. Monsoon trough, the northward shift of the ITC, creates a trough of low pressure known as the monsoon trough. This trough serves as a conduit for the movement of moist air from the southern hemisphere to the northern hemisphere. Indian Ocean influence. The warm waters of the Indian Ocean provide a source of moisture. As the monsoon trough approaches the Indian Peninsula, it draws in moisture-laden air from the Indian Ocean. Barrier of the Western Ghats. The Western Ghats, a mountain range along the western coast of India, acts as a barrier. Moist monsoon winds hit the mountains, are forced to rise, cool, and condense, leading to heavy rainfall on the windward side, southwest side of the mountains. Effect of YNSO on the Indian monsoon. El Niño events, characterized by warmer than average sea surface temperatures in the central and eastern Pacific Ocean, can disrupt atmospheric circulation patterns and lead to suppressed monsoon rainfall, contributing to drought conditions and agricultural losses. Conversely, La Niña events, marked by cooler than average sea surface temperatures in the same region, tend to enhance the monsoon by intensifying atmospheric circulation, resulting in increased moisture inflow and higher than normal precipitation over India. Thus, El Niño and La Niña, collectively YNSO, exert a significant influence on the Indian monsoon. These interlinked oceanic and atmospheric phenomena underscore the intricate nature of the monsoon system and emphasize the need for understanding and predicting their occurrences to effectively manage the resultant impacts on agriculture, water resources, and regional economies. Amidst growing unpredictability driven by climate change and altered oceanic dynamics, understanding and addressing climate impacts on the monsoon is crucial. Through scientific inquiry, technology, and community engagement, we can navigate this evolution, preserving its vital role in environmental renewal and societal well-being. Extra edge. Key elements propelling the commencement of the Indian monsoon season. Differential heating. Rapid heating of the Indian landmass during summer creates a low-pressure area that attracts moist air from the surrounding ocean. Shift of ITCZ. The northward shift of the ITC. During summer brings it closer to the Indian subcontinent, resulting in the convergence of moist air and the buildup of atmospheric moisture. Tibetan Plateau. The intense heating of the Tibetan Plateau generates a thermal low-pressure area, drawing in moist air from the Indian Ocean and facilitating the inflow of monsoon winds. Indian Ocean currents. The warm waters of the Indian Ocean provide ample moisture and energy to the atmosphere, crucial for sustaining the monsoon winds and rainfall. Topography effects. The presence of geographic features like the Western Ghats influences wind patterns, causing orographic rainfall and aiding in the spread of monsoon rains. Q198. In recent years, India has witnessed an increase in extreme weather events. Assess the factors contributing to this trend. 15 marks, 250 words, Core demand of question, write the factors contributing to the increasing extreme weather events in India. Write suitable way ahead in this regard. ANS. In recent years, India has been grappling with an upsurge in extreme weather events, ranging from intense heat waves to unprecedented rainfall leading to floods. Such phenomena not only disrupt daily life, but also pose substantial threats to agriculture, economy, and biodiversity. For example, extreme weather-related events caused 573 disasters in India between 1970 and 2021 that claimed 138,377 lives. Factors contributing to increased extreme weather events in India. Global warming. Rising average global temperatures attributed to increasing greenhouse gas emissions have been triggering heat waves and altering rainfall patterns in India. For example, India experienced temperatures reaching up to 50 degrees Celsius in some parts during summers. Deforestation. The loss of forest cover in the Himalayan region has increased the risk of landslides and flash floods. Similarly, the destruction of mangrove forests along the coastlines has reduced the natural protection against cyclones and storm surges. Ocean atmospheric phenomena. Anomalies in phenomena like El Niño, which is a periodic warming of the Pacific Ocean that affects rainfall distribution across the globe. For example, in 2015-16, India faced one of its worst droughts in decades due to a strong El Niño event. Land use changes. Alteration in land use for activities such as mining affects the natural climate-regulating mechanisms of the environment. For example, coal mining in Jharkhand has led to land degradation, water contamination, and GHGs, which can affect the local and regional climate. Melting glaciers. Due to rising temperatures, glaciers are retreating at an alarming rate, threatening the water security and livelihoods of millions of people downstream. For example, in 2013, a massive flood triggered by a glacial lake outburst killed thousands of people in Uttarakhand. Wetland degradation. The destruction of wetlands, which act as buffers during floods, have left regions more vulnerable to extreme rainfall events. For example, Chennai faced severe flooding in 2015 due to the encroachment and conversion of wetlands into residential and commercial areas. Loss of biodiversity. It can reduce the ecosystem's resilience to extreme weather events, making recovery from such events more difficult. For example, a study found that the loss of coral reefs due to bleaching and disease reduced the coastal protection and fishery productivity in Lakshadweep. Way ahead. Mitigation strategies. India can take inspiration from the success of the National Solar Mission, which set ambitious targets for solar energy capacity. For example, the Ujjwala Yojana is a model for extending the reach of clean cooking fuels, reducing reliance on polluting alternatives. Climate-resilient infrastructure. Learning from the Surat Climate Adaptation Project, which strengthened the city's infrastructure against flooding, other vulnerable regions can invest in similar measures. Early warning systems. India's cyclone warning division's accurate predictions and timely evacuations, as seen during Cyclone Phelan in 2013, exemplify the importance of early warning systems. Expanding such capabilities to various extreme weather events is essential. Sustainable urban planning. For instance, Ahmedabad's Sabarmati Riverfront Development Project showcases the integration of green spaces within urban planning. The project not only beautifies the city, but also enhances resilience against floods and heat waves. Reforestation. The success of the Billion Tree Tsunami project by UNEP demonstrates the potential of large-scale reforestation efforts. India can implement similar projects, focusing on native tree species, to restore ecological balance. Sustainable agricultural practices. The zero-budget natural farming model, popularized by Subhash Palekar, emphasizes chemical-free, climate-resilient farming practices. Widespread adoption of such practices can transform Indian agriculture. Conservation of wetlands. Chilika Lake in Odisha, a Ramsar wetland of international importance, showcases how wetland conservation can coexist with sustainable tourism, benefiting both biodiversity and local economies. Community awareness. The Chipko movement in Uttarakhand, where villagers hug trees to protect them from deforestation, remains an iconic example of grassroots environmental awareness and activism. Biodiversity conservation. Other states can learn from the success of the Periyar Tiger Reserve in Kerala, where local communities participate in conservation efforts and ecotourism, highlighting the potential of community-led biodiversity conservation. Going ahead, by understanding and adapting to these extreme weather events, India can not only safeguard its populace, but also nurture a harmonious relationship with its diverse and rich environmental heritage. This journey would be a testimony to the synergic coexistence of development and nature, treading a path of resilience and sustainable growth. Q199. Critically assess the relationship between El Niño Southern Oscillation, ENSO, events and the Indian monsoon. 15 marks, 250 words, core demand of question. Write the relationship between El Niño Southern Oscillation, ENSO, events and the Indian monsoon. Write the impact of this relationship between the ENSO events and the Indian monsoon. Write suitable way ahead in this regard. ANS. El Niño Southern Oscillation, ENSO, occurs due to a periodical variation in temperatures between the ocean and atmosphere in the east-central equatorial Pacific. It has two phases: El Niño, characterized by warmer ocean temperatures, and La Niña, characterized by cooler ocean temperatures. It significantly influences weather patterns globally, including the Indian monsoon system. Relationship between ENSO events and the Indian monsoon. Rainfall patterns. During the ENSO phenomena, the Indian subcontinent experiences altered rainfall patterns. E.g., the severe drought in 2002 was due to a strong El Niño event. Conversely, the 1988 monsoon was one of the wettest on record, a direct effect of La Niña. Onset timing. The onset of the monsoon can be significantly affected by ENSO events, a classic example being the delayed onset in 2014 due to El Niño influences, which disrupted the agricultural calendar extensively. Regional variations. ENSO events foster significant regional disparities in weather conditions across India. For instance, during the 2006 El Niño, while central India experienced a dry spell, northeast India faced heavy floods due to irregular rainfall patterns. Monsoon depressions. La Niña encourages more monsoon depressions, as seen in 2010, resulting in a better-than-average monsoon season with bountiful rains, which, while aiding agriculture, also brought about challenges like flooding in several regions, including Punjab and Haryana. Historical events. For instance, El Niño events of 1877 and 1899 affected Indian monsoon, reducing rainfall and caused severe droughts, showcasing a consistent pattern of distress during such periods. Understanding this historical trend is crucial for modern predictive and preparatory strategies. Adversaries from the relationship between ENSO events and the Indian monsoon. Food security. During ENS events, particularly El Niño, the rainfall patterns in India become erratic, which directly affects food security. For example, the El Niño event in 2002 resulted in a substantial decline in food grain production, affecting the food security of millions. Water scarcity. Water scarcity becomes a pertinent issue in El Niño years. For example, the year 2016 was marked with acute water shortages in various parts of India, necessitating even train services to transport water to the affected areas. Biodiversity. Changing monsoon patterns have adverse effects on biodiversity. For example, the Western Ghats, a biodiversity hotspot in India, witnessed severe disruptions in the ecosystems during the El Niño years, leading to loss of species and altered migration patterns. Energy sector. Hydroelectric power generation, which is a significant contributor to India's energy sector, faces challenges due to irregular water availability. For example, during 2023 summers, partially an El Niño year, power demand has touched the record height of 233 gigawatts. Rural livelihoods. Rural populations, chiefly reliant on agriculture, face the brunt of ENSO events. For example, the farmer distress witnessed in various states during 2002 and 2009 were largely due to the El Niño phenomena affecting the monsoons adversely. Inflation. Agricultural output fluctuations lead to inflation, affecting the daily life of common people. For example, during the 2009 El Niño event, India witnessed a surge in the prices of essential commodities, burdening the common man with increased costs due to its double-digit inflation rate, 10.88%. Way ahead to overcome adversaries. Improved forecasting. Learning from Australia's Bureau of Meteorology, which utilizes state-of-the-art computational facilities to forecast weather patterns, India can further modernize the IMD with higher computational prowess for accurate predictions during UNSO events. Water conservation. Israel's success story in water management through desalination and recycling of wastewater can serve as a benchmark. India can develop policies promoting these technologies to sustain water resources during erratic monsoon periods induced by UNSO events. Ex-Sujalam campaign. Agricultural adaptation. Taking cue from the SRI, System of Rice Intensification, method, which proved successful in Tamil Nadu, promoting such innovative agricultural practices nationally could enhance productivity despite adverse climatic conditions. International cooperation. Collaborating with initiatives like the Global Climate Observing System, GCOS, can help in assimilating data and research to better understand the UNSO events and devise strategies at a global level. Leveraging technology. Promoting the development and use of genetically modified GM crops that are resistant to fluctuating weather conditions. Additionally, developing mobile apps to advise farmers on the best practices during varying climatic conditions. The El Niño Southern Oscillation, UNSO, events have a profound impact on the Indian monsoon, affecting various sectors in India, including agriculture, biodiversity, and health. Adopting these strategies, India can pave a forward-thinking path in managing the impacts of UNSO events on its monsoonal patterns, focusing on sustainability and resilience in various sectors. Q200. Discuss the characteristics and meteorological significance of Western disturbances in the Indian subcontinent. 10 marks, 150 words, core demand of question, etc. Mention the characteristics of Western disturbance in different headings like origination, movement. Explain the meteorological significance of Western disturbances on Indian subcontinent. ANS. Western disturbance is an extratropical storm, which gives rain to North and Northwest India during winter. It is very useful for wheat and winter crops. It is driven by westerlies, which are prevailing winds from the west toward the east in the middle latitudes between 30 and 60 degrees latitude. Characteristics of Western disturbances. Origin. Western disturbance originates from Mediterranean Sea, Black Sea, and Caspian Sea. It is formed due to a temperature gradient caused by the mixing of warm air from the tropics and cold air from the northern polar regions. Movement. The disturbance travels from the western to the eastern direction. It moves across the Middle East from Iran, Afghanistan, and Pakistan to enter the Indian subcontinent. Upon its arrival in Pakistan and northern India, clouds along with rain and snow also arrive. Seasonal impact. While they are active throughout the year, their influence is more pronounced during the winter months. On an average, India receives 4 to 6 intense Western disturbances a month, between December and March. Effect on temperature. A migrating Western disturbance is preceded by warm, moist air and is followed by cold, dry air. This keeps the temperatures warm in the peak winter months of December and January and stops the temperature from rising in February and March. Precipitation. Western disturbances, specifically the ones in winter, bring moderate to heavy rain in low-lying areas and heavy snow to mountainous areas of the Indian subcontinent. They are the cause of most winter and post-monsoon season rainfall across Pakistan and northwest India. Relationship with other weather systems. Western disturbances can interact with other weather systems, such as tropical cyclones and the Indian monsoon, resulting in complex weather patterns. Meteorological significance of Western disturbances. Winter rainfall and snowfall. Precipitation due to Western disturbances and associated dynamics are termed as Indian winter monsoon, IWM. Western disturbances are responsible for winter rainfall and snowfall in the northern regions of India. It is also vital for replenishing groundwater and essential for river systems. 30% of annual precipitation over the northwest Indian region is received during winter, and it is mostly associated with Western disturbances. Impact on monsoon season of India and neighboring countries. Western disturbances play a crucial role in the onset and progression of the Indian monsoon. They can cause variations in the monsoon rainfall pattern, leading to droughts or floods in different parts of India and neighboring countries like Pakistan, Nepal, and Bangladesh. Agricultural impact. Change in onset of Western disturbances leads to variation in sowing of rabi crops, particularly in the regions that lack irrigation facilities. Similarly, delayed withdrawal could lead to a late harvest, exposing crops to excess rains leading to losses. Untimely rains in India lead to a lower wheat production of 102.9 metric tons in the 2022-23 agriculture year. Air pollution. Western disturbances can impact the air quality of the regions they affect. During winter, Western disturbances can cause an increase in air pollution levels due to the burning of fossil fuels for heating purposes. In March 2023, almost all spells of smog in Delhi NCR region coincided with Western disturbances. Temperature and precipitation patterns. Western disturbances can influence the precipitation and temperature patterns in the regions they affect. They can cause a drop in temperature due to rainfall and snowfall and alter the precipitation patterns, leading to waterlogging and soil erosion. Thus, the Western disturbance has a significant impact on the weather patterns of the regions it affects, including winter rainfall, monsoon rains, and snowfall in the Himalayan region. There is evidence to suggest that the intensity of Western disturbances is increasing, leading to more extreme weather events such as heavy rainfall and snowfall. This makes the understanding of Western disturbance crucial for weather forecasting and disaster preparedness. Q201. Discuss the natural resource potential of the Deccan Trap. 10 marks, 150 words, core demand of question. Briefly explain the natural resource potential of the Deccan Trap. ANS. Situated in west-central India, the Deccan Traps form an expansive volcanic plateau that extends over a substantial area of the Deccan Plateau. This geological feature holds significance not only for its vastness, but also for its distinctive geological composition, which offers valuable insights into the Earth's volcanic history and potential natural resources. Key aspects of the Deccan Trap's natural resource potential. Minerals and ores. The volcanic origins of the Deccan Traps have endowed them with a diverse array of minerals and ores. Predominantly composed of basalt, this geological formation harbors valuable deposits including zeolites, calcite, quartz, manganese, bauxite, iron, and occasionally precious gems like diamonds. These mineral riches have sparked keen geological interest and spurred exploration endeavors. Agriculture and soil fertility. The volcanic eruptions shaping the Deccan Traps deposited nutrient-rich volcanic soils, fostering fertile agricultural lands. Supporting diverse crops such as cotton, soybeans, pulses, and sorghum, these soils showcase the region's robust agricultural capacity. Water resources. The Deccan Traps comprise interconnected basaltic layers, serving as natural reservoirs that store groundwater. These geological structures play a vital role in augmenting the region's water resources, fulfilling agricultural and domestic water requirements effectively. For example, in Maharashtra, India, the basaltic layers of the traps act as aquifers, storing groundwater that is utilized for irrigation, drinking water supply, and other domestic purposes in the region. Geothermal potential. The Deccan Traps harbor significant geothermal energy reserves. Heat from subsurface magma can be tapped for power generation. For example, the Unkeshwar geothermal field showcases this potential. Hydroelectricity generation. The topography of the Deccan Traps, featuring plateaus and river valleys, facilitates hydroelectric power production. For example, the rivers like the Godavari and Krishna, originating in the Western Ghats, offer hydroelectricity prospects. Timber and medicinal flora. The Western Ghats forests within the Deccan Traps abound in valuable timber and medicinal plants. These resources are utilized for traditional medicine, construction, and furniture manufacturing. For example, the teakwood and medicinal herbs found in the region. While the Deccan Traps present diverse natural resource prospects, their utilization demands responsible and sustainable practices. Striking a balance between resource extraction and conservation is imperative to safeguard the environment and uphold the welfare of local communities for generations to come. Q202. How can technology contribute to the sustainable utilization of soil resources? 10 marks, 150 words, core demand of question. Describe the role of technology in achieving sustainable soil resource utilization. ANS. Soil resources are a form of environmental asset providing a range of ecosystem services. Soil resources comprising minerals, organic matter, water, and life are vital for agriculture and ecosystems. Amid escalating environmental challenges of degradation, erosion, and nutrient depletion, the quest for solutions gains momentum. Among these, technology's rising prominence stems from its high potential for sustainable soil resource utilization, as elaborated below. Technology's role in achieving sustainable soil resource utilization. Precision agriculture. Precision agriculture harnesses technology to optimize farming practices according to specific soil conditions and crop needs. GPS-guided machinery and variable rate technology enable accurate nutrient application, minimizing waste and boosting yields. For example, research indicates that precision agriculture can reduce fertilizer use by up to 30%, curbing nutrient runoff. Soil monitoring and analysis. Technology-driven soil monitoring ensures well-informed decisions. For example, IoT-based soil moisture sensors exemplify this, allowing precise irrigation control. Effective soil moisture management, facilitated by such sensors, can lead to yield improvements of around 10–15%. Soil mapping. Digital soil mapping through technology provides comprehensive insights into soil variability. For example, platforms like USDA's Soil Data Mart facilitate targeted efforts for conserving soil. Such detailed mapping has demonstrated the potential to decrease sediment loss by up to 50% and nutrient runoff. Soil health management. Soil health management, aided by technology, promotes balanced ecosystems. For example, techniques like DNA sequencing guide the selection of cover crops that nurture beneficial microbes. Notably, cultivating diverse microbial communities could enhance crop yields by approximately 10–20%. Similarly, use of biofertilizers and nanotechnology, like nano-urea, can help in soil health management by promoting responsible nutrient management. Digital platforms for knowledge sharing. Digital platforms facilitate knowledge exchange for effective soil management. For example, platforms such as Climate FieldView furnish real-time data, enabling data-driven decisions. Reports indicate that farmers engaging with such platforms are significantly more inclined to adopt sustainable soil practices. Soil carbon sequestration. Technology plays a key role in enhancing soil carbon storage for climate resilience. For example, tools like Comet Farm estimate the impact of practices on carbon sequestration. Conservation practices facilitated by technology could potentially elevate soil carbon storage by 25% to 60%. Smart irrigation systems. Smart irrigation systems, driven by technology, optimize water utilization. For example, soil moisture sensors integrated into drip systems exemplify this approach, conserving up to 40% of water while simultaneously enhancing yields by around 20%. Precision irrigation, supported by technology, can lead to water use reductions ranging from 15% to 30%. Soil erosion prediction and prevention. Technology plays a pivotal role in predicting and preventing soil erosion. For example, utilizing tools like the revised Universal Soil Loss Equation, RUSL, aids in assessing erosion risks. Implementing erosion control practices guided by RUSL can lead to substantial reductions in soil loss, potentially reaching up to 90%. Soil rehabilitation. Modern technology is helpful in restoring soil health, fertility, and sustainability through innovative methods. Further, advanced sensors and data can optimize cover crops for improved structure, nutrient retention, and weed control. For example, research by the SARE program underscores technology's role in successful soil rehabilitation, showing a remarkable 25% increase in soil organic matter content over time. The convergence of technology and soil resource management offers promising avenues for sustainability. However, challenges of data privacy and accessibility need addressing. Looking ahead, bridging the digital divide and uniting human ingenuity with technological advancements will pave the way for a more sustainable agricultural future. Extra edge. Remote sensing. Remote sensing with satellite imagery and drones plays a pivotal role in soil condition monitoring. By identifying erosion-prone areas, satellite data empowers strategic conservation initiatives. Studies suggest that remote sensing can enhance soil erosion prediction accuracy by up to 80%. Research highlights that adopting conservation tillage practices may lead to impressive reductions of soil erosion, ranging from 50% to 90%. According to a study conducted by the International Erosion Control Association, bioengineering methods can reduce erosion rates by up to 90% compared to conventional methods. GPS-guided precision land leveling techniques significantly curtail soil erosion. Precision planting and monitoring revive soil through efficient crop rotation. Q203. Evaluate the hydro energy potential of India and elucidate the reasons behind its limited spatial distribution. 10 marks, 150 words, core demand of question. Discuss the hydro energy potential of India. Highlight the reasons behind its limited spatial distribution. Provide a suitable way forward in this regard. ANS. Hydro energy, also known as hydroelectric energy or hydropower, is a renewable energy source generated by the kinetic energy of flowing water. As of 2023, India boasted a hydroelectric capacity of 46,850 megawatts, constituting approximately 11.2% of the nation's total power generation capacity. This figure underscores the substantial potential for hydro energy in India. Hydro energy potential of India. Estimated potential. India possesses an estimated hydropower potential of 145,320 MW, excluding small hydro projects, SHBs, which contribute an additional 20 gigawatts potential. At a 60% load factor, this potential can meet the demand of around 85,000 megawatts. Regional distribution. The primary regions with significant hydropower potential are in the northern and northeastern parts of the country. Arunachal Pradesh leads the way with the largest untapped potential of 47 gigawatts, followed by Uttarakhand with 12 gigawatts. River systems. The unexploited potential is concentrated along three major river systems: the Indus, Ganges, and Brahmaputra. These regions hold immense promise for hydropower development. Pumped storage potential. India boasts more than 90 gigawatts of pumped storage potential, with 63 identified sites officially recognized in national energy policies. These sites play a crucial role in providing valuable grid services and enhancing energy grid stability. Reasons for limited spatial distribution of hydro energy in India. Regional variability. The distribution of water resources is uneven across different states and regions of India. The Himalayan region in the north and northeastern states receive heavy rainfall and are endowed with abundant water resources, making them suitable for hydroelectric projects. However, other regions, such as the arid western and some peninsular parts of India, have limited water resources, restricting the scope for hydro energy development. Interstate water disputes. India's federal structure has led to disputes over the sharing of river waters between states. Interstate water disputes can delay or even stall the implementation of hydro projects, reducing their spatial distribution. For example, the Kaveri water dispute between Karnataka and Tamil Nadu exemplifies this. High capital costs. Hydroelectric projects require substantial upfront capital investments for dam construction, turbines, and transmission infrastructure. Access to financing and the ability to mobilize resources can be challenging, particularly for economically disadvantaged regions, limiting the spread of hydro energy development. For example, the Dibong hydropower project in Arunachal Pradesh is estimated to cost 31,876.39 rupees crore at the May 2021 price level. Technological challenges. Some regions lack the necessary technical expertise and infrastructure to support hydro energy projects. For example, the remote Himalayan regions, for instance, face logistical challenges in transporting equipment and materials to construction sites. Social and environmental concerns. The construction of large dams and reservoirs for hydroelectric projects often raise social and environmental concerns, including habitat disruption, waterlogging, and the displacement of local communities, limiting the expansion of hydro energy initiatives. For instance, construction of the Sardar Sarovar Dam led to the rise of Narmada Bachao Andolan due to concerns about environmental degradation and displacement of local communities. India possesses substantial hydro energy potential, but its spatial distribution is hindered by multiple factors. India's ambitious goal of achieving 40% of its installed capacity from non-fossil fuel sources by 2030 emphasizes the significance of tapping into this potential. Through cooperative and determined endeavors, India can turn this aspiration into reality, fostering a cleaner and more diverse energy landscape, thereby securing a sustainable energy future for the nation. Q204. Discuss the distribution of mineral resources in India and highlight the key environmental concerns that mining regions often grapple with. 15 marks, 250 words, core demand of question. Provide the distribution of mineral resources in India. Discuss the key environmental concerns with which mining regions grapple. ANS. Mineral resources refer to naturally occurring substances found within the Earth's crust that have economic value and are extracted for various industrial and societal purposes, such as metallic and non-metallic minerals. India boasts rich mineral reserves, with over 20,000 known deposits and recoverable reserves of more than 60 minerals. However, mine operations are heavily concentrated, with 11 states, Andhra Pradesh, Odisha, Chhattisgarh, Jharkhand, West Bengal, Maharashtra, Tamil Nadu, Gujarat, Madhya Pradesh, Rajasthan, and Karnataka, hosting 90% of operational mines. Distribution of mineral resources in India. The distribution of mineral resources in India can be categorized into three major mineral belts. Northeastern Plateau Region. This region includes Kota Nagpur in Jharkhand, the plateau areas of Odisha, parts of West Bengal, and a portion of Chhattisgarh. It is known for its rich deposits of raw materials used in steel production, such as iron ore, coal, manganese, and bauxite. Mica is also abundant in this region, contributing to the manufacturing industry. The presence of these minerals has led to the establishment of numerous steel mills in the area. Southwestern Plateau Region. The states of Karnataka, Goa, the highlands of Tamil Nadu, and Kerala make up the Southwestern Plateau Region. This region is rich in bauxite and ferrous metals like iron, ore, and manganese. Limestone is another significant mineral found in this region, supporting industries like cement production. Northwestern Plateau Region. The Aravalli Mountains in Rajasthan and parts of Gujarat, particularly areas with Darwar rocks, form the northern Western Plateau region. Valuable metals such as zinc and copper are abundant in this region. Rajasthan is known for its ample reserves of sandstone, granite, and marble, making it a preferred destination for construction projects. The Himalayan region in northern India also hosts minerals like copper, lead, zinc, cobalt, and tungsten. Key environmental concerns with which mining regions grapple. Deforestation. Mining operations often lead to extensive deforestation, resulting in the clearance of forests for mining activities, which disrupts local ecosystems and reduces carbon sequestration capacity. For example, in the state of Chhattisgarh, vast swathes of lush forests have been cleared to make way for coal mining. Landscape damage. Mining alters the natural topography of an area, causing changes such as soil erosion, loss of natural habitats, and visual degradation, which impact the local environment and communities. For example, as demonstrated by the Singhbhum region of Jharkhand. Air pollution. Mining activities release a range of airborne pollutants, such as dust, particulate matter, and potentially harmful gases, which significantly degrade air quality and pose health risks to both human and animal populations in mining regions, for example, the coal mining operations in Jharia, Jharkhand. Water contamination. Mining runoff, which carries toxic chemicals and heavy metals, infiltrates nearby water bodies, contaminating both groundwater and surface water sources and thus poses a threat to aquatic life as well as to the communities dependent on them. For example, a study in the Western Ghats of Kerala highlighted the water pollution and adverse impacts on aquatic ecosystems resulting from mining activities. Biodiversity loss. Mining operations often result in habitat destruction and fragmentation, displacing or destroying native flora and fauna, leading to a loss of biodiversity in affected regions and potentially threatening endangered species. For example, in the Western Ghats, mining activities have led to the decline of several critically important wildlife habitats, including the Myristica swamps unique to the region. Greenhouse gas emissions. Mining activities emit greenhouse gases through the use of fossil fuels for machinery and transportation, as well as from the release of methane from coal mines, contributing to global climate change and its associated impacts. For example, India holds the third position in global emissions from coal mining, with estimated emissions of 22 mtCO2e in 2020 and projections to reach 45 mtCO2e by 2050. India possesses vast and diverse mineral riches concentrated in specific regions of the country. Nevertheless, the extraction of these resources frequently exacts a considerable environmental toll. Confronting these challenges requires a holistic approach that integrates responsible mining practices, robust regulatory measures, and sustainable resource management to safeguard the enduring welfare of both its natural ecosystems and its burgeoning economy. Q205. How does soil erosion manifest multifaceted consequences? significantly affecting agricultural productivity and disrupting the delicate environmental balance in the distinctive context of India. 10 marks, 150 words, core demand of question. Describe the multifaceted consequences of soil erosion and relate them with the agricultural productivity and the environmental/ecological balance. Substantiate with relevant examples, statistics, or case studies. Suggest innovative measures to combat soil erosion in India. OnlyIAS soil erosion is a natural process where soil is transported from one location to another by the action of wind, water, or ice. While this phenomenon has been occurring for millions of years, human activities have significantly accelerated its rate in recent centuries. India, in particular, faces a substantial challenge as it loses about 5,334 million tons of soil annually, which is 16 times higher than the global average, highlighting the severity of the problem because of the far-reaching consequences of soil erosion. Multifaceted consequences of soil erosion. Impact on agriculture and environment. Reduced soil fertility. Soil erosion strips away nutrient-rich topsoil, leading to decreased fertility and hampering crop productivity. For example, intensive farming in Punjab's Green Revolution areas has caused significant soil degradation, reducing crop yields over time. As a result of reducing fertility, Punjab's wheat production has already declined from 178 lakh metric in 2017-18 to 149 lakh metric tons in 2021-22. Soil compaction. Intensive farming practices can compact the soil, reducing water absorption capacity and increasing surface runoff. This limits root growth and water infiltration, resulting in waterlogging and decreased crop yields as seen in some parts of Gujarat. Sedimentation in water bodies. Eroded soil particles carried into rivers and lakes cause sedimentation, reducing water storage capacity and degrading water quality. For example, an immigration officer harboring prejudice against certain nationalities. For example, the Sardar Sarovar Reservoir in Gujarat is an example where sedimentation affects water storage and hydropower generation. Loss of arable land and landscape changes. Soil erosion converts fertile land into unproductive wastelands, threatening food security and agricultural sustainability. For example, Rajasthan has seen vast agricultural lands transformed into unproductive wastelands due to accelerated erosion. Disruption of biogeochemical cycles. Soil erosion leads to the loss of essential nutrients and organic matter, altering biogeochemical cycles and affecting nutrient availability for plants and other organisms. This disruption impacts forest ecosystems as seen in the Western Ghats. Waterlogging and drought. Erosion alters soil water holding capacity, causing waterlogging in low-lying areas and increased drought susceptibility elsewhere. For example, in the Gangetic Plains, erosion has led to waterlogged fields during the monsoon, affecting rice cultivation. Water pollution. Eroded soil carries agrochemicals and pollutants into water bodies, harming aquatic organisms and disrupting food webs. For example, pesticides and fertilizers from eroded soil in Punjab's rivers have contributed to water pollution and affected fish populations. Soil biodiversity loss. Erosion reduces soil biodiversity, impacting soil health and ecosystem resilience, creating a feedback loop. For example, loss of microbial communities due to degrading soil health in the eastern Himalayas is affecting forest soil health and nutrient recycling. Measures required. Nanotechnology in soil stabilization. Incorporating nanosilica particles in soil can improve its strength and stability, reducing erosion risks in construction sites and agricultural fields. Soil bioengineering techniques. Bioengineering techniques with live plants can effectively control erosion in hilly terrains and help in restoring soil health, as exemplified by the construction of check dams in Uttarakhand. Soil carbon sequestration. Implementing soil carbon sequestration practices like agroforestry can improve soil fertility and contribute to carbon sequestration, helping in climate change mitigation, as seen in some parts of Andhra Pradesh. Big data and AI for erosion prediction. Using AI and satellite data to predict erosion-prone regions allows farmers to take preventive measures and adopt suitable conservation practices as seen in Maharashtra, where a project called Smart Villages uses AI and satellite data to predict erosion-prone regions. IoT-based soil moisture monitoring. Utilizing IoT-based soil moisture sensors to optimize irrigation prevents waterlogging and erosion in agricultural fields, as done by Karnataka during its digital greenhouse project. Drones for precision soil conservation. Drones equipped with multispectral cameras can monitor soil erosion and plan targeted conservation efforts in ecologically sensitive areas, as exemplified by their use by the Gujarat government. Soil erosion-resistant crop varieties. Developing erosion-resistant crop varieties like the Gujarat Rice Variety 2, GRV2, suitable for areas prone to erosion ensures sustainable agriculture. Hydrogel-based soil amendments. Adopting hydrogel-based soil amendments improves soil structure and water retention, reducing erosion risks and enhancing crop productivity, as evident in Tamil Nadu, where farmers are using hydrogel-based soil amendments. Geospatial technologies for land use planning. Utilizing geospatial technologies as done by Kerala for land use planning and zoning minimizes erosion-prone activities near water bodies. Aquatic vegetation. Using aquatic vegetation to control erosion protects aquatic ecosystems and prevents sedimentation. For example, the Chilika Lake Conservation Program in Odisha has successfully used aquatic vegetation to control erosion, protect the lake's ecosystem, and prevent sedimentation. Urban farming. Encouraging urban farming on rooftops promotes sustainable agriculture and reduces erosion while conserving soil resources exemplified by the Green Roof initiative in cities like Bengaluru. Agroforestry and vegetative cover. Planting trees, shrubs, and cover crops along with agricultural crops helps anchor soil, reducing erosion caused by wind and water. For example, Miyawaki method. Soil erosion poses significant challenges to India's agriculture and environment, threatening food security and disrupting ecological balance. However, through the convergence of traditional wisdom and modern advancements, India can safeguard its precious soil resources, secure its agricultural future, and maintain a harmonious coexistence with nature. Extra edge. Soil erosion hotspots. Certain regions in India, like the Western Ghats and Eastern Himalayas, are more prone to erosion due to their fragile landscape, leading to large-scale habitat degradation of native species, ultimately causing huge biodiversity loss. The National Bureau of Soil Survey and Land Use Planning, NBSS and LUP, estimates that soil erosion extends to about 119.2 million hectare area in India. This is about 35% of the total land area of India. Additionally, soil erosion is costing India about 1% of its GDP every year. Q206. Forest resources in India are greatly substantial and impactful for achieving SDGs 2030. Comment on the context in the light of accompanied challenges and measures to resolve them. 10 marks, 150 words, core demand of question. Mention about the significance of forest resources in India for achieving SDGs 2030. Enumerate the challenges faced in conservation of forest resources in India. Suggest measures to overcome these challenges. ANS. According to India's State of Forest Report, 2021, India has forest on around 24% of geographical area. Forests provide numerous tangible and intangible benefits that could pave the way for achievement of SDGs outlined in 2015. Forest resources in India are impactful for achieving SDGs 2030 in following ways. Poverty alleviation, SDG 1, no poverty, and SDG 8, decent work and economic growth, are supported through activities such as sustainable harvesting of non-timber forest products like honey, bamboo, and medicinal plants. Sustainable agriculture, SDG 2, zero hunger, can be achieved by promoting agroforestry and incorporating sustainable forest management techniques. Biodiversity conservation. Forests support various endangered species such as the Royal Bengal tiger, and conserving them will contribute to SDG 15, life on land. Climate change mitigation. The agroforestry initiative in Haryana promotes tree plantation in agricultural lands, reducing carbon emissions, thus contributed to SDG 13, climate action. Water conservation, SDG 6, clean water and sanitation, can be achieved by protecting forested areas, such as the Western Ghats, which act as water catchment areas and provide clean water to millions. Renewable energy, SDG 7, affordable and clean energy, can be addressed by promoting sustainable forest-based bioenergy projects, like biomass power plants, that reduce dependence on fossil fuels. Sustainable tourism, Promoting responsible tourism in such areas supports SDG 8, decent work and economic growth, and SDG 12, responsible consumption and production. Challenges faced in conservation of forest resources in India. Development pressure. The construction of infrastructure projects like dams and highways often requires clearing large forest areas, leading to habitat loss for wildlife and disruption of ecosystems. For example, clearing of RE forests for Mumbai Metro. Deforestation. For instance, the conversion of forests into agricultural land in states like Assam and Madhya Pradesh threatens forest resources. Illegal logging. Unregulated logging for timber and fuelwood leads to forest degradation. The rampant illegal logging in the state of Jharkhand endangers valuable forest resources. Forest fires. Forest fires, often caused by human activities or natural causes, contribute to forest loss and degradation. For example, recurring forest fires in Uttarakhand and Himachal Pradesh. Wildlife poaching and trafficking. The poaching of tigers in the Sundarbans or the illegal trade of endangered species like pangolins in northeast India are prime examples. Invasive species. The proliferation of invasive species like Lantana camara in the Nilgiri biosphere reserve affects forest diversity and regeneration. Lack of community involvement. The lack of community involvement in the Bani grasslands of Gujarat affects the sustainable use of forest resources for community benefits. Measures to overcome these challenges. Effective implementation of FRA, 2006. To illustrate Kangar Gadi National Park in Chhattisgarh, where it has been fully implemented, resulted in positive impact. Promoting community engagement. The Joint Forest Management Program in India encourages local communities to participate in decision-making and benefit sharing. Example involving Guddi and Gujar tribes in Himalayan states. Strict enforcement of anti-logging measures. The creation of special task forces like the Forest Protection Forces in various states of India has been effective in curbing illegal logging. Encouraging reforestation and afforestation. Promoting reforestation initiatives, such as planting native tree species and restoring degraded forests, can help in replenishing forest resources. For example, the Green India Mission. Strengthening international cooperation. Collaborating with international organizations and neighboring countries can facilitate the exchange of knowledge, resources, and best practices. These measures, if implemented effectively, can help address the challenges faced in forest resources conservation in India, ensuring the preservation and sustainable management of this vital natural asset, as well as contribute towards achievement of SDG 2030. Q207. Examine the perspective of geothermal energy as a renewable and sustainable source in India, highlighting various challenges in its widespread adoption. 10 marks, 150 words, core demand of question. Brief about the potential of geothermal energy as a renewable and sustainable source in India. Mention various challenges in its widespread adoption. ANS. Geothermal energy is a renewable and sustainable energy source that harnesses heat from the Earth's crust to generate electricity and heat homes. It has the potential to provide a significant source of clean energy for the future. Potential of geothermal energy as a renewable and sustainable source in India. Abundant resource. India has substantial geothermal energy resources due to its location in a seismically active region. The country has an estimated potential of 10,600 megawatts of geothermal energy. Baseload power. It provides a reliable and consistent baseload power supply, unlike intermittent sources like solar and wind. It can contribute to grid stability and reduce dependence on fossil fuels. Hot springs and geysers. India is home to several geothermal hot springs and geysers that can be harnessed for power generation. For example, the Puga geothermal field in Ladakh has a high potential for geothermal power development. Direct use applications. Geothermal energy can be utilized directly for applications such as space heating, greenhouse cultivation, and industrial processes. For example, in Chumathang, geothermal energy is used for heating houses and for hot water supply. District heating. Geothermal district heating systems can be implemented in cities, providing efficient and sustainable heating. For example, the city of Manikaran in Himachal Pradesh is known for its geothermal district heating system. Tourism potential. Geothermal sites, with their unique geological features and hot springs, can attract tourists and contribute to local economies. For example, The hot springs in Tadapani, Himachal Pradesh, are a popular tourist destination. Off-grid applications. Geothermal energy can be particularly beneficial for off-grid areas or remote regions where access to conventional energy sources is limited. It can provide electricity for remote villages, reducing reliance on diesel generators. For example, remote areas like Ladakh, etc. Various challenges in its widespread adoption. High upfront costs. The initial investment required for geothermal power projects are substantial. Drilling deep wells and installing geothermal infrastructure can be expensive, deterring potential investors. Limited geothermal resources. India has limited access to high-temperature geothermal resources, which are most suitable for power generation. Most of the geothermal fields are low temperature and may only be viable for direct heat applications. For example, the Puga geothermal field in Ladakh has low temperatures. Lack of technical expertise. Developing geothermal projects require specialized knowledge and expertise. India currently lacks a significant number of professionals with experience in geothermal exploration and development. Regulatory and policy framework. The absence of a comprehensive regulatory and policy framework specifically tailored for geothermal energy hampers its growth. Uncertain resource assessment. Accurate assessment of geothermal resources is crucial for project viability. However, limited exploration and data availability make it difficult to assess the potential of geothermal sites accurately. Infrastructure limitations. In remote areas where geothermal resources may be available, the lack of infrastructure adds to the overall costs and complexity. Environmental considerations. Geothermal projects may have negative environmental impacts, such as potential groundwater contamination or seismic activity. However, these challenges need to be addressed through collaborative efforts, research and innovation, financial incentives, etc. to promote geothermal energy as a viable and sustainable option in India's energy mix. Q208. Delineate the concept of data as the new oil, and provide a perspective on India's position in harnessing and leveraging data for socio-economic development and the challenges faced. 10 marks, 150 words, core demand of question. Discuss the concept data as the new oil. Mention about India's position in harnessing and leveraging data for socio-economic development. Highlight the challenges faced by India in this regard. ANS. Data is the new oil because it is a valuable resource that drives innovation and growth. It is being harnessed by companies to drive decision-making, develop new products and services, and gain a competitive edge in the marketplace. It powers the modern industries the way oil has supported the industries of the 20th and early 21st century. Concept of data as the new oil. Value resource. For example, companies like Google and Facebook collect vast amounts of user data, which they analyze and monetize through targeted advertising, generating significant revenue. Extraction and refining. Similar of extracting oil from the ground, data is collected through various sources such as social media, online transactions, sensors, and more. This raw data is then refined and processed to extract meaningful insights and patterns. Economic power. Companies that effectively gather and utilize data gain a competitive advantage, similar to oil-rich nations in the global economy. For example, Netflix leverages user viewing patterns to recommend personalized content. Privacy concerns. Just as the extraction and use of oil have environmental consequences, data collection raises privacy concerns as it can lead to data breaches, identity theft, and surveillance. India's position in harnessing and leveraging data for socio-economic development. Aadhaar. India's biometric-based unique identification system. Aadhaar has revolutionized access to government services and welfare programs by enabling targeted service delivery and reducing corruption. Digital payments. Today, India has become the world's leading country in terms of UPI transactions, promoting a cashless society. For example, in 2022, India witnessed 74 billion UPI transactions worth 126 lakh crore. E-governance. Initiatives like Digital India and online portals like MyGov and e-tendering have enhanced transparency and efficiency in governance. Healthcare data. Projects like the National Health Stack and National Digital Health Mission aim to create a comprehensive digital health ecosystem that enhances disease surveillance, monitors public health, and improves healthcare access. Crop yield optimization. Through the use of data analytics, satellite imagery, and weather data, farmers can now optimize crop yields, reduce input costs, and mitigate risks through platforms like Cropin and AgriStack. Smart cities. Cities like Surat and Pune are utilizing data analytics for efficient waste management, traffic optimization, and improved citizen services. Startup ecosystem. Companies like Flipkart, Paytm, and Zomato utilize data-driven insights for personalized user experiences, targeted marketing, and efficient logistics. Education initiatives. Initiatives like the National Education Policy, NEP, and online learning platforms leverage data to enhance access and quality of education, ensuring personalized instruction and identifying areas for improvement. Social impact initiatives. Organizations like DataKind and Dasra are driving data-driven social impact projects in India by using data analysis to address social challenges, such as education inequality, healthcare disparities, and poverty eradication. Challenges faced by India in this regard. Data accessibility. For instance, in healthcare, fragmented health records across different hospitals and clinics make it challenging to derive comprehensive insights for public health initiatives. Data quality. For example, inaccurate or incomplete data in agricultural surveys can lead to ineffective policies and suboptimal resource allocation in the farming sector. Digital divide. Unequal access to technology and internet connectivity creates a digital divide, limiting the benefits of data-driven initiatives to certain segments of society. For example, according to iCube 2020, 58% of men and 42% of women in India uses internet. Skill gap. A shortage of skilled professionals proficient in data analytics, data science, and data management affects the effective utilization of data. For example, India in 2021 had 1.3 million digitally skilled professionals and faces a shortage of 0.5 million such professionals. Interoperability. Data interoperability issues arise due to inconsistent formats and systems used by various organizations, which limits the seamless integration and exchange of data across sectors. Data silos. Siloed data within different government departments, organizations, and sectors restricts the comprehensive analysis and utilization of data. For example, land data and income data lying with different departments. Ethical considerations. For example, ensuring fairness and transparency in algorithms used for credit scoring or recruitment processes is vital to prevent discrimination and promote inclusive growth. Addressing these challenges requires a multifaceted approach involving investments in technology, policy reforms, capacity building, and public-private collaborations. By overcoming these hurdles, India can harness the power of data for inclusive and sustainable socio-economic development. Q209. Highlight the significance and challenges associated with the exploration and extraction of polymetallic nodules in the Indian Ocean for India's resource security. 10 marks, 150 words, core demand of question. Highlight the significance of the exploration and extraction of polymetallic nodules in the Indian Ocean for India's resource security. Discuss about the challenges associated with the exploration and extraction of polymetallic nodules ANS. Polymetallic nodules are potato-shaped structures found on the seabed that contain high concentrations of valuable metals like nickel, copper, cobalt, and manganese. Recently, the government of India signed a 15-year contract with ISA for exploration of polymetallic nodules in the central Indian Ocean basin. Significance of the exploration and extraction of polymetallic nodules in the Indian Ocean for India's resource security. Ensures energy security. Even the 10% recovery of 380 MMT polymetallic nodules in the central Indian Ocean can meet India's energy requirement for next 100 years. Rare earth materials. They contain rare earth materials like cerium, erbium, etc., which are essential for various high-tech industries, and their availability ensures India's self-sufficiency in advanced technologies and reduces dependence on imports. Energy transition support. Polymetallic nodules are rich in cobalt, a crucial component for lithium-ion batteries used in electric vehicles and renewable energy storage systems. Reduced imports and trade deficits. India is one of the largest importers of minerals. Domestic extraction of polymetallic nodules can help reduce the import bill. For example, according to OEC, India in 2022 imported $291 billion in mineral products, mainly from Iraq, Saudi Arabia, Russia, etc. Technology and expertise development. India's involvement in this sector will foster technological innovation and skill development, enhancing the country's capabilities in deep-sea mining. For example, deep-sea mission launched by India for deep-sea exploration, rare earth metals commercial exploitation, discovery of metals and polymetallic nodules in the Indian seabed. Diversification of resource base. By exploring and extracting these nodules, India can diversify its resource base, reducing its dependence on traditional mineral sources. Strategic resource reserves. By actively exploring and extracting polymetallic nodules, India can establish strategic resource reserves, ensuring long-term availability of critical minerals. Employment opportunities for coastal communities, especially for those dependent on traditional sectors like fishing, by enabling them to participate in deep-sea mining operations. Challenges associated with the exploration and extraction of polymetallic nodules. Technological complexity. Deep-sea mining vessels with the necessary capabilities and expertise are scarce, and India would need to invest heavily in acquiring or developing such infrastructure. Environmental impact. Deep-sea mining activities can have significant environmental consequences, including habitat destruction and disruption of marine ecosystems. Financial investment. It requires substantial financial investment, including research and development, exploration, and infrastructure setup. For example, Cabinet Committee on Economic Affairs approved the proposal of Deep Ocean Mission at an estimated cost of 4,077 rupees crore for a period of 5 years. Geopolitical competition. Several countries, including China, Japan, and South Korea, have expressed interest in exploring and extracting polymetallic nodules. Market volatility. India's resource security could be influenced by these market dynamics, affecting the economic viability of deep-sea mining operations. Overall, the exploration and extraction of polymetallic nodules in the Indian Ocean offer India an opportunity to enhance its resource security, support its energy transition, strengthen its geopolitical position, and fulfill the vision of Atmanirbhar Bharat. But for that, the above-mentioned challenges needs to be tackled. Q210. Analyze the perspective of green hydrogen as a sustainable energy solution for India. Mention the stumbling blocks attached to it and the necessary resolutions required to promote its widespread adoption in the country. 15 marks, 250 words, core demand of question. Highlight the potential of green hydrogen as a sustainable energy solution for India. Discuss about the challenges in promoting its widespread adoption in the country. Highlight the measures required to promote its widespread adoption in the country. ANS green hydrogen refers to hydrogen gas produced through a process called electrolysis using electricity generated from renewable energy sources. The National Green Hydrogen Mission has set up a target of 5 million tons per annum, MTPA, of green hydrogen production by 2030. Potential of green hydrogen as a sustainable energy solution for India. Renewable energy storage. Excess solar energy can be used to produce hydrogen through electrolysis during the day and then converted back to electricity during the night, tackling the challenge of intermittent renewable energy sources. Decarbonizing transportation. India's ambitious plan to introduce fuel cell electric vehicles, FCEVs, for public transportation like buses and taxis can greatly benefit from green hydrogen. For example, recently Indian Oil unveiled India's first green hydrogen run bus that emits just water. Industrial applications. Industries such as steel, cement, and chemicals require vast amounts of high-temperature heat, which can be provided by green hydrogen. Off-grid power generation. For instance, hydrogen fuel cells can be deployed to provide clean energy for off-grid communities or telecom towers. Clean cooking and heating. Green hydrogen can replace fossil fuels like LPG and coal for cooking and heating purposes. Green ammonia production. Ammonia, a key ingredient in fertilizers and industrial processes, can be produced using green hydrogen, contributing to sustainable agriculture and reducing carbon footprints. Challenges in promoting its widespread adoption. High production costs. The cost of renewable energy sources used for electrolysis can be high, making green hydrogen production more expensive than conventional hydrogen production from fossil fuels. For example, The current cost of green hydrogen production in India is $4.50 per kilogram. Limited production capacity. The current capacity for green hydrogen production is relatively low compared to the growing demand. Regulatory and policy framework. Inconsistent or unclear regulations can create barriers and uncertainty for investors. Infrastructure development. Building an extensive network of hydrogen refueling stations and retrofitting existing infrastructure can be costly and time-consuming. For example, to become successful, green hydrogen mission will need an investment of 8 rupees lakh crore. Lack of standardization. Developing common standards and certifications for green hydrogen is essential to ensure interoperability and build trust in the market. Geographical limitations. For example, arid regions like Western Rajasthan with limited access to water resources may struggle to produce hydrogen through electrolysis. Necessary measures required to promote its widespread adoption. Invest in research and development. Allocate funding for research and development initiatives to enhance the efficiency and cost-effectiveness of green hydrogen. Build infrastructure. Countries like Japan and Australia have developed hydrogen supply chains to facilitate the transportation of hydrogen across long distances. Support pilot projects and demonstrations. The European Commission's Fuel Cells and Hydrogen Joint Undertaking funds various projects, including hydrogen-powered trains and buses. Financing and investment. Governments and international financial institutions can provide financial support, such as the European Commission's funding for hydrogen projects through the Innovation Fund. Promote international cooperation. The International Partnership for Hydrogen and Fuel Cells in the Economy aims to accelerate the global deployment of hydrogen technologies. Foster public-private partnerships. For example, the India Hydrogen Alliance aims to promote the commercialization and adoption of hydrogen and fuel cell technologies. Going ahead, green hydrogen holds immense potential for India as a sustainable energy solution. Overcoming these challenges and promoting widespread adoption of green hydrogen aligns with the country's goals under the Paris Agreement and contributes to a sustainable and low-carbon future. Q211. Explain the pivotal role of soil fertility in shaping the cropping patterns in different regions of India. Also discuss the relationship between soil health and sustainable agriculture practices in India. 15 marks, 250 words, core demand of question. Discuss the role of soil fertility in the determination of cropping patterns in different regions of India, along with examples. Discuss relation between soil health and sustainable agriculture practices. OnlyIAS. Soil fertility refers to the ability of soil to provide essential nutrients and support plant growth. India's geography showcases a rich tapestry of diverse soil types, spanning alluvial plains, lush coasts, arid landscapes, hilly terrains, the Central Plateau, and northeastern states. Role of soil fertility in the determination of cropping patterns in different regions of India. North Indian plains. Clayey soils with moisture retention require specific practices like puddling and transplantation used in paddy cultivation. For example, fertile alluvial soils in Uttar Pradesh support paddy and wheat cultivation, while Bihar focuses on rice and Uttar Pradesh on wheat. Coastal regions. Agricultural practices include adapting to saline conditions through appropriate irrigation techniques and soil amendments. For example, coastal sandy soils as in Gujarat are exposed to salt water. Salt-tolerant crops like rice, coconut, and cashew are cultivated. In areas like Kerala, salt-tolerant rice varieties are grown. Western arid regions. Arid region soils, such as the sandy soils of the Thar Desert in Rajasthan, have low water holding capacity. Agricultural practices in arid regions include water management techniques like drip irrigation and the use of drought-resistant crop varieties. For example, drought-tolerant crops like millets, pulses, and oilseeds such as pearl millet, mung, and moth are preferred in arid regions such as Rajasthan. Eastern hilly regions. Hilly regions like Arunachal Pradesh have diverse soils influenced by altitude and geology. Tea, coffee, spices, and fruits are cultivated, such as tea in Darjeeling. Agricultural practices adapt to varying fertility, slopes, and drainage, utilizing techniques like terrace farming to prevent erosion. For example, tea, coffee, spices, and fruits are cultivated, such as tea in Darjeeling. Central Plateau. Agricultural practices involve utilizing the soil's high fertility and moisture retention capacity through proper irrigation and soil management techniques to enhance crop productivity. For example, black cotton soil in the Vidarbha region of Maharashtra is fertile and supports crops like cotton, sorghum, and pulses. Similar black soil regions in Madhya Pradesh also cultivate cotton. Northeastern states, hilly regions with abundant rainfall, like the Brahmaputra Valley in Assam, have diverse soil fertility. Agricultural practices adapt to specific soil fertility, with Sikkim employing traditional organic farming techniques for sustainable agriculture. For example, crops such as rice, tea, jute, and fruits are grown, including tea in Darjeeling, West Bengal. Soil health and sustainable agriculture practices in India. Soil health encompasses the physical, chemical, and biological properties of the soil. It encompasses the overall condition and capacity of the soil to sustain and support various ecosystem functions and services. Sustainable agriculture practices aim to enhance productivity while minimizing environmental harm. It encompasses methods and approaches that aim to meet the current needs of food and fiber production while preserving the environment, supporting rural communities, and ensuring the ability of future generations to meet their own needs. Relationship. Nutrient management. Healthy soil supports nutrient availability and crop growth in sustainable agriculture through practices like balanced fertilization, organic matter incorporation, and biofertilizer use. Soil conservation. Healthy soils needs prevention of erosion and preservation. Agricultural practices like contour plowing, terracing, and mulching, which protect soil, maintain structure, and enhance water and nutrient retention, gives better productivity. Water management. Healthy soils needs optimized water use. Agriculture practices like drip irrigation, rainwater harvesting, and water-efficient crops enhances productivity and sustainability. Biodiversity and soil health. Maintaining soil health through practices like crop rotation, agroforestry, and cover crops promotes biodiversity and ecological balance in sustainable farming. Soil carbon sequestration. Sustainable agriculture practices like agroforestry and the use of cover crops can sequester carbon in the soil, helping mitigate climate change and improving soil health by enhancing its organic matter content. Supporting rural livelihoods. By promoting sustainable agriculture practices, India's farming communities can achieve more stable and sustainable livelihoods. Healthy soils can lead to higher crop yields, reducing the vulnerability of farmers. However, currently India is facing following challenges in harnessing this relationship. Soil degradation. Unsustainable practices cause erosion, wind erosion in Rajasthan, nutrient depletion, e.g. Punjab, and salinization, parts of Gujarat. Water scarcity and irrigation challenges. Inefficient flood irrigation, Gangetic Plains, leads to water wastage, while climate change exacerbates water scarcity, e.g. Maharashtra's Marathwada. Climate change impacts. Rising temperatures affect soil moisture, e.g. Telangana. Extreme weather events disrupt soil structure, e.g. Bihar, and changing rainfall patterns impact nutrient availability, e.g. Karnataka. Pests, diseases, and weed management. Improper pesticide use causes pest resistance, e.g. pink bollworm in Maharashtra, and monocropping spreads diseases, e.g. stem rust in Punjab's wheat. Limited access to resources and technology. Smallholder farmers face constraints in adopting sustainable practices due to limited access to affordable organic fertilizers and technology, e.g., precision agriculture tools. The diverse soil types, nutrient composition, and fertility levels require farmers to tailor their agricultural practices to optimize productivity. By understanding and harnessing the unique characteristics of the soil in each region, farmers can ensure sustainable and productive agriculture, contributing to food security and economic growth. Q212. Analyze the assertion, demographics is destiny. In light of India's emergence as the world's most populous nation, discuss the potential opportunities presented by this demographic evolution in the aging world. 10 marks, 150 words. Core demand of question populous nation. Mention the implications of this assertion in light of India's emergence as the world's most. Suggest the potential opportunities presented by this demographic evolution in the aging world. ANS. The assertion demographics is destiny is based on the idea that the age, gender, and ethnic structure of a population can influence various aspects of the society, including its economic growth, political landscape, cultural norms, and social progress. In the context of India's emergence as the world's most populous nation, this phrase has several implications. Implications of this assertion in light of India's emergence as the world's most populous nation. Economic growth. India's large population and burgeoning middle class present an enormous market for goods and services. This growth is already evident in sectors such as e-commerce, with companies like Flipkart and Amazon investing heavily in the Indian market. Global influence. As the world's most populous nation, India's diplomatic and strategic importance on the global stage could increase. For example, it could push for more representation in international bodies such as the UN Security Council. Urbanization. India's population growth is accompanied by rapid urbanization, creating opportunities for infrastructure development. The Smart Cities mission aims to develop sustainable and inclusive cities, showing the country's commitment to leveraging this trend. Education. A large young population also demands quality education. While this is a challenge, it has also spurred innovation in edtech, with companies like Wallah making learning more accessible and engaging. Environmental impact. A larger population also means increased resource consumption and environmental impact. However, this challenge can spur India towards more sustainable practices, as we've seen with the push for solar energy and electric vehicles. Agriculture. With more mouths to feed, pressure on agriculture increases. However, this also presents an opportunity to employ modern agricultural practices and agri-tech solutions, as seen in the growth of companies like Dahat. Potential opportunities for India presented by this demographic evolution in the aging world. Labor force. With an average age of 28, India has a sizable young population ready to enter the workforce, unlike aging societies like Japan or Germany. However, this demographic dividend must be capitalized on through proper skill development. Outsourcing services. India has already established itself as a leading destination for outsourcing services due to its cost competitiveness and large English-speaking workforce. With the aging populations in many developed countries, it may increase further. Manufacturing hub. Given its abundant labor supply, India has the potential to become a global manufacturing hub. The Make in India initiative was launched with this vision to make India a global manufacturing powerhouse. Healthcare sector. Despite the youthfulness of its population, India has a rapidly growing healthcare sector. As the world's elderly population grows, India could become a leading provider of affordable healthcare services, pharmaceuticals, and medical devices. Cultural influence. With its growing population and the proliferation of internet connectivity, the Indian culture and entertainment industry could see a wider global impact. For example, Bollywood movies gaining global recognition and Indian series trending on Netflix. Digital services. The country's young population is technologically savvy, providing a big market and testing ground for digital services. This has been evident with the success of digital payment systems like Paytm and UPI in India. India's demographic dividend, with its young, vibrant population, presents a promising future. With strategic focus on education, healthcare, infrastructure, and technology, India will not only cater to its own economic needs, but also contribute significantly to the global economy in an aging world. Q213. Enumerate the factors which have prerogative in carving the rural-urban divide, considering the emerging population dynamics of India. 10 marks, 150 words, core demand of question. Factors having prerogative in carving the rural-urban divide. Give some measures to fill the gap. ANS. The rural-urban divide highlights socio-economic and demographic disparities, including variations in infrastructure, basic services, and economic opportunities. Cities like Mumbai and Delhi offer better facilities, while rural districts like Madhubni, Bihar, and Baraik, Uttar Pradesh, face limited infrastructure and job prospects. Factors having prerogative in carving the rural-urban divide. Economic opportunities. Rural to urban migration is fueled by job and income disparities, leading to migration from rural areas to IT hubs like Bengaluru or Gurugram. Infrastructure and basic services. Urban areas like Mumbai and Delhi offer superior access to healthcare, education, transportation, and services due to well-developed infrastructure and advanced facilities. Education and skill development. Urban areas provide quality education and skill enhancement opportunities, attracting rural students to enroll in renowned institutions like IITs and IMs. Agricultural dependence. Rural agricultural challenges prompt migration to urban areas for better livelihoods, exemplified by outmigration of farmers from drought-prone regions in rural Maharashtra. Example as per Economic Survey, 2021-22, the average monthly income per agricultural household in the country stood at 10,218 rupees in 2019. Industrialization and urbanization. Urban industrial growth creates job opportunities, attracting migrants to cities like Surat in Gujarat and Chennai in Tamil Nadu for employment within thriving industries. Social factors. Social aspirations and lifestyle changes drive rural to urban migration as young adults from rural areas pursue cosmopolitan lifestyles and career opportunities in cities. Government policies. Urban development policies like SEZs and the Delhi-Mumbai Industrial Corridor impact population dynamics by attracting migrants with job prospects and improved infrastructure. Technological advancements. Technological advancements in cities like Hyderabad and Pune create demand for skilled workers, attracting talent from rural regions with IT sector expertise. Following measures can help us to fill the rural-urban divide. Rural business incubators. Support rural entrepreneurs with resources and mentorship. For example, DAY NRLM. Skill development for rural youth. Equip rural youth with job-relevant skills. For example, PM Kaushal Vikas Yojana. Integrated rural development. Adopt a holistic approach to address multiple sectors for rural development. Digital connectivity. Expand internet access in rural areas for online services and opportunities. Sustainable agriculture practices. Promote eco-friendly farming and value addition. For example, Paramparagat Krishi Vikas Yojana, PKVY. Community-based development. Empower local communities in decision-making and resource mobilization. Bridging the rural-urban divide in India's population dynamics is essential for a prosperous and equitable future. Through collaborative and forward-looking approaches, India can create a more inclusive society where individuals from all backgrounds have access to quality education, healthcare, and livelihood options. Q214. Enumerate the key impediments in utilizing the young and dynamic demography of India. How can they be utilized for holistic development of the nation? 10 marks, 150 words, core demand of question. Mention about the key impediments in the utilization of full potential of Indian demography. Suggest ways through which THS demography can be utilized for holistic development of the nation. ANS. India, the world's most populous country with over 1.4 billion people, possesses a young and dynamic demography. With more than 50% of the population in the productive age group, 15-59 years, India's demographic composition presents diverse implications for various sectors of the nation's development. India encounters numerous obstacles in effectively harnessing its youthful and dynamic demographic potential. Key impediments: inadequate education and skill development. Limited access to quality education and skill development programs hinder the utilization of India's young population. A UNICEF report from 2019 reveals that approximately 47% of Indian youth will have the essential education and skills needed for employment by 2030. Unemployment and underemployment. Inadequate job opportunities present obstacles for India's expanding workforce. For example, India's unemployment rate was 8.1% in April 2024, CMIE data. Limited access to quality healthcare. Inadequate healthcare infrastructure and disparities in access affect the well-being of the young population. Socio-economic inequalities. Income disparities and unequal resource distribution hinder opportunities for India's young demography. For example, India's richest 1% population owns 40% of total wealth. Rural-urban divide. Disparities in education, healthcare, and employment opportunities exist between rural and urban areas. Gender inequality. Gender disparities hinder women's empowerment and workforce participation. Lack of infrastructure and basic amenities. Insufficient infrastructure limits economic opportunities for the young population. For example, a World Bank report estimates that India will need to invest $840 billion over the next 15 years in its urban areas to meet the demand. Digital divide. Limited access to technology and internet connectivity creates disparities in digital skills and opportunities. For example, Indian women are 15% less likely to own a mobile phone and 33% less likely to use mobile internet services than men. Measures: enhance education, skills, and entrepreneurship. There is a need to strengthen curriculum, vocational training, and support startups for improved employability, as India's employable talent sees a significant increase, jumping from 46.2% to 50.3% in the India Skills Report 2023. Promote job creation and digital transformation. Implement sector-specific initiatives to promote digital literacy and leverage technology for job prospects. For example, improving formal skill training, as only 5% of our workforce is formally trained. Ensure gender equality and inclusion. Empower women through education, skill development, and entrepreneurship opportunities. For example, institutionalization of period leave in all government and private offices. Facilitate policy reforms and regulatory ease. Simplify regulations, create a business-friendly environment, and encourage ease of doing business. For example, early rollout of new industrial policy 2022. Strengthen social safety nets and collaboration. Provide unemployment benefits, skill upgradation programs, and foster public-private partnerships for job creation. For example, a quasi-minimum basic income for vulnerable sections of society can be considered. Enhance financial inclusion and sustainable development. Promote financial literacy, access to capital, green skills, and sustainable practices for future job opportunities. India's young demography is a valuable asset that can drive growth and development. By investing in education, skills, entrepreneurship, and sustainable practices, India can unleash the potential of its youth and create a prosperous future. Collaboration and strategic investments are essential for harnessing the demographic dividend.